Three, two, one, and away we go. Okay, so welcome again to another pre-recorded lecture. Hopefully the last one. Yeah, so what's the plan? All right, well, we are jumping back in the textbook now. We are jumping back to chapter 2. Where we will now talk about how all of this fun stuff that we have been working on tells us how to solve linear systems of equations. So again, remind ourselves what they are. Right, a system of linear equations is anything that looks like this. So you have a collection of m equations that have n unknown variables, and so the idea here is that the a's are all known, and so are all of the b's, and the question is figure out what the x's need to be. All right, now, this is the main thing we care about in this class. We want to know how to solve these, and how to solve comes with a couple of things, right? So first of all, does this even have an answer, right? If you're talking about how to solve something, the first thing you want to do is make sure it actually has an answer, right? You don't go hunting dragons unless you know a dragon actually exists. Okay, right, and then furthermore, if you do know dragons exist, how many? Right, so all of that, when we say solve, this linear system is all wrapped up in that. Right. So we started the course off by working with these and doing row operations and kind of getting a feel for how do they work exactly and all that other fun stuff. And we got kind of a punchline of solutions always look like a very specific type of thing, a solution to the homogeneous plus a solution to plus a particular solution. Okay. And sort of the insufficient explanation that we got of why that's the answer and why it looks like that kicked off, all right, well, let's enter the world of vector spaces and build up a whole bunch of material about dimension and talk about linear mappings. And the reason for all of that is all of that comes back to systems and gives us not only just a full-out solution, but a really very precise and clear explanation of here's what you do to solve these things. All right. So let us talk about that. So the first thing to note is that if you're hearing some weird noises, that's the cough drop in my mouth. One of the reasons why I'm doing only just a pre-recorded lecture today, so I only have to do this song and dance once. Okay. All right. So this matrix equation then is the same thing as the linear system of equations, right? The whole point of matrix multiplication, the way we built up how do you multiply matrices, was built up the dot product because we noticed, hey, these are really dot products in disguise on the left-hand side. So indeed, this system of equations can really be rewritten as a matrix equation, specifically AXB, where X contains all of the unknown things we're looking for. A is just the coefficient matrix for the system, as we've previously discussed, and the B is the right-hand side. So this is really nice if you really look at this, because this has m equations in it, so there are m equal signs. This is one equation with one equal sign. It is automatically better because of that. But it's also automatically better because rewriting your system of linear equations in this form immediately allows us to start applying everything that we have worked on and discussed. Indeed. So hopefully the first thing that you recognize is, oh hey, I want my b to equal a times x for some x. Where have we seen that before? All right, but before we get into that, let's just do a nice explicit example so you have a feel for kind of how this goes down. Right, here is a nice system of equations, and here is the matrix equation that it can be rewritten as. So, right, again, note, get your coefficient matrix. So the first column here corresponds to all of the x variables. So there's only one, so we get a 1. This column is all of the y variables, so there are 2. All of the z variables is the third one, so you pick up the 3, 6, and 8. Note that this matrix times this vector, first row dot product with first column, indeed is equal to that. Second row dotted with this column gives me that. And a third row dot product with this column gives me that. So indeed, and that all lines up with those numbers on the right hand side. So yeah, it all checks out. It all tracks. It's all good. All right. So yeah, every system of linear equations can be turned into a nice matrix equation, and AX equals B. Okay. So now that we know that every system can be rewritten in that form, we can now begin applying all of the fun stuff that we have set up and talked about when it comes to matrices. So the first thing to note, of course, is that matrix multiplication is a linear mapping. So A times X is a linear mapping from Rn to Rm. And any solution to the matrix equation, right, so if you've got A and B and an X satisfying, it gives you a matrix equation. There are two possibilities going on here. So this right here represents a linear, the output of the linear transform that takes elements from Rn and spits out elements of Rm. If B is not in the column space, so in other words, if B is not in the range of the linear mapping, then this matrix equation has no solution, right? The set of solutions are the things so that A times X is actually equal to some B. So the set of elements B that can actually have that happen, the elements in the column space, right? If you're not in the column space, then this matrix equation cannot have a solution. Okay, so again, let's repeat that. Every matrix induces a linear mapping from Rn to Rm. A solution is any element of Rn so that A times X actually is equal to B. So the natural thing to do then is, all right, well, the only possible way I can have a solution is if B is equal to an A times X, which means that B must be in the column space. So again, remember, the X's are what we're looking for. The A and the B are fixed, right? They're already set in stone before you get into this problem. Okay, so A and B are already locked down, so I can immediately just ask, well, is B in the column space? If B fails to be in the column space, then there is no hope of solving this. Right. If B is not in the column space, but I can find an X that makes this work, well, then B would be in the column space, and that's contradictory. All right. So right off the bat, we've got a super easy test to tell us if we actually have a solution or not that does not care about what X is, right? It just simply is asking, does this live in this set? If it does, then hooray, we can actually find a solution. If it doesn't, then there is no solution, and in that case, the system is just then called inconsistent. So there we go. Right, we now have a yes or no, an on-off switch to tell us, okay, when do solutions actually happen? Okay, if your B does not belong to the column space of your matrix, so note, B is not a linear combination of the columns, then the matrix equation cannot have a solution. All right. Okay, so when we're trying to solve a linear system and you find yourself in this situation that you have something that does not belong to the column space, that means there is no solution, but that doesn't mean the story's over. We will get to that. Probably next week we'll start talking about, okay, let's see you have an inconsistent system. You don't just throw your hands up and walk away. There are some things you can do, and we'll get into that. So what we'll focus on for the majority of this week and the beginning of next week is what happens when you actually have something that lives in the column space. All right, well, if you are in the column space, that means there is an X satisfying this. That's what it means to be in the column space. So that means the matrix equation has at least one solution. Okay, so right off the bat, we are put into two possibilities. You have a matrix and you have a vector B out of Rm. If you're in the column space, the system, no solution. If you're in the column space, we know there is at least one answer. All right, so now our goal is to sharpen that. Okay, so if you are in the column space, we have at least one answer. We know that if you have two answers, you have to have infinitely many. Okay, so now what we want to do is focus on the following. If you're in the column space, when can we make this stronger than just at least one solution? When can we make that a unique solution? All right. So that's great. So note what we've done. 4 slides into this, we have now completely repurposed all of the material that we've been talking about, all of that vector space stuff, all of that linear transform stuff, right? And we've been able to rework that language into, hey, if I want to talk about solving linear systems, I'm really talking about solving this matrix equation, which is really asking a question about what does the range of this linear mapping look like? So, hey, that's really nice. So, there you go. Okay, and the good news is that we spent a lot of time talking about how linear mappings behave, so asking questions about what does the range do, like, oh, I don't know what the dimension of the range would be, which is, oh, I don't know the rank of the matrix. Yeah, it's all coming back around. That's quite nice. Okay. All right, so that being said, let's get into it. And before we fully get into it, let's add one little extra thing to say. So yeah, a system that actually has a solution is usually referred to as consistent, although inconsistent is usually a little bit more exciting. Right? That's the one where it's like, ooh, the traditional method does not have an answer. What do you do here? All right. So for right now, we're uninterested in that case, and so we'll focus on the things that are in the column space. And as I was kind of already setting up, so if you're in the column space, it means you have an answer. The question now is, can we guarantee unique? And the answer in general is, yeah, you can, so long as your matrix is behaving. And specifically, the behaving in this case is the matrix has full rank. Remember, full rank means that the rank of the matrix is n, the number of columns. And again, remember, rank is the dimension of the column space. So if the dimension of your column space is the number of columns you have, then these solutions are unique. So let's see that in action. So let's actually prove that. Okay, so let B be in the column space. So if you're in the column space, that means there is a solution to your matrix, to your linear system of equations. So there is an x, so that ax is equal to b. That is, by definition, what the column space is. All right. So what we want to verify now is that if there is another solution, it actually has to equal x. Yeah. So take another y that's a solution to ax equals b. All right. Well, ax is equal to b, ay is equal to b, so ax is equal to ay. Now, what we want, of course, is to cancel a to get x is equal to y. But as we've already stressed repeatedly, cancellation of matrix multiplications is not allowed in general. So there has to be a reason why you can do it. There has to be a reason why you can do it. All right. So note that when you subtract this over and factor out an a, you get this. And now you've got, oh, hey, a minus x must belong to the null space. But by assumption, we have full rank, and as we've discussed, full rank happens only when the null space is trivial. So, hey, since x minus y must live in the null space, must equal 0, which means x must equal y. So yes, we are actually allowed to cancel a here. The full rankness of the matrix lets us get away with that. So that is amazing. So now we have seen, right, so this proof here is really nice. So first of all, it gives us an answer to, hey, when does a system of linear equations have a unique solution? Well, if the coefficient matrix has full rank, then yes. Anything that's in the column space, the only elements that can actually produce solutions, then the solution that you find must indeed be unique. So a system of linear equations has a unique solution, provided that the matrix is full rank and the element on the right-hand side actually lives in the column space. So, yay, that's very nice. So we get a nice answer then for a pretty natural question of when do systems of linear equations have a unique solution. So we have conditions now for that, if the matrix is full rank and the element B is in the column space. Cool. And note the proof technique, again, revealed something to us. It gave us a nice condition to ensure that matrix multiplication actually can be canceled. So now we actually see hidden within this proof is this idea that full rank matrices can be canceled in terms of matrix multiplications. So we'll probably make that a lot more precise in the next set of slides when we talk about, invertible matrices. Okay, beautiful. So, all right, we now have that if you are full rank and B lives in the column space, then you have a unique solution. So, what about the reverse, right? Let's say we know that AX equals B always has a unique solution. All right. Well, if it has a solution, then by default, B must be in the column space. Now, does unique solutions ensure that full rank must be happening? So in other words, is this a necessary and sufficient condition for unique solutions? The answer is yes, but we got to get there. Before we get there, let's recontextualize something. Homogeneous linear systems, remember those were the ones where the right-hand side was all zeros. So in other words, homogeneous linear systems are any matrix equation of the form AX equals 0. And, oh hey, isn't that just the null space? It is. Isn't that just portraying the public trust? There's a reference somebody will understand. Except for, like, the real human brains will get that one. Let's say that. All right. Anyway, so yeah, the homogeneous linear systems, which we, again, if you let your mind float back, when you're trying to solve a system of linear equations, the first thing you want to do is actually solve the homogeneous case, and then find a particular solution. So again, what we did in differential equations, because again, what we were doing in differential equations was really linear algebra in disguise. All right. So, yes. So, to help us along here, we'll just refer to this as the homogeneous system for the matrix A. And again, note that solutions to this are precisely the elements of the null space of the matrix. So I've already made reference to this multiple times. Here it is actually being formally set up and described. So, yes, every homogeneous linear system of equations is just this matrix equation in disguise, and so the solutions thereof are just the elements of the null space. So we have now seen the two fundamental subspaces of matrices in action, right? We've seen the column space in action, and now we're seeing the null space in action. Cool. All right. So, what we want to prove is that unique solutions ensure that you must have full rank. So what we'll first do is tackle the case of the homogeneous systems. Okay, so if you've got a matrix and its homogeneous system has unique solution, then the rank must be full. So in other words, the rank is the number of columns. Okay, right, so again, we're looking for the converse of this. If you have full rank, then you have unique solutions. So what we want to prove is that unique solutions will guarantee full rank. So giving us a complete characterization of when unique solutions need to happen, only when the matrix has a full rank. All right, so first we're going to take care of the homogeneous case, and then we'll bootstrap this up to any matrix equation. Okay, so suppose that the homogeneous system has a unique solution, then A must have full rank. Okay, and just like the previous result, this is just a recontextualizing of stuff we've already proven. Okay, so the first thing to note is that 0 is always a solution to the homogeneous. So if you let your mind float back, we already talked about how the homogeneous system of linear equations can always be solved, just everything equals 0. Right, and that's hopefully now even more clear and apparent because the solution set to the homogeneous system is the null space, which is a subspace, which means it has to have 0 in it. All right, so if we want to verify uniqueness, then we need to verify that anything in the null space is just the 0 vector. All right. Yeah. All right, well, if you're in the null space, then AX is equal to 0, and our hypothesis that the homogeneous system has a unique solution forces X equaling 0. That means the null space has to be trivial. The null space being trivial, of course, means that the rank is full. And so the proof is over. Yay! So again, this proof here is not too exciting in the sense that it's got some new technique or a new idea on display. It really doesn't, right? It's really just, here are things we've already proven, but we're just giving them a different context. That's quite nice. All right, so let's actually prove something interesting. Okay, which is the following. So the non-zero solutions to a homogeneous system are called non-trivial solutions, right? Homogeneous equations always have 0 as a solution, so anything else would be bright interesting. So we'll call those the non-trivial solutions. So as we will now prove, the only way for such a thing to exist is if the rank is strictly less than n. So in other words, non-trivial solutions exist only when we are not full rank. Excellent. That's pretty cool. All right. So let's do it. So suppose that you actually have a non-trivial solution to the homogeneous system. All right, well, if my rank was full, then the null space would be trivial, but that can't happen, right? By hypothesis, we have something in the null space that is not equal to 0, so the null space cannot be trivial. Right, so that means the rank cannot equal n, and as we've proven, rank does not exceed n, hence why rank equaling n we refer to as full rank. So it's got to be that the rank is actually strictly less than n. It's not equal to n, and it's less than or equal to it. That is by definition strict. Okay, so if there is a non-trivial solution, then the rank is strictly less than n. Okay, that is the forward direction. Now we want the reverse. Suppose that the rank actually is strictly less than n. Then let's verify that there is a non-trivial solution floating around. Okay. Okay, well, by the rank nullity theorem, we have the following. Rank of A is strictly less than n, but that's equal to the rank of A plus the dimension of the null space. Subtract these off, we then get the dimension of the null space is strictly positive, so that means the dimension of the null space is at least 1, so I can find at least one non-zero thing in the null space. Anything in the null space is a solution, since it's coming out of linearly independent, it must be non-zero. Hey, a non-zero solution to the homogeneous system is now found. And there we go. That's it must be a non-trivial solution. Beautiful. Okay. All right, so again, remember, our goal right now is to prove what? We're trying to prove that a system of linear equations has a unique solution only when the matrix is full rank. We've proven that full rank gives you unique solutions, and now we're going the reverse way, unique solutions forces full rank. So our first task was to address the case of the right-hand side equaling 0, which is the homogeneous, and we have now proven that the homogeneous has a unique solution only when the rank is full. If the rank is less than n, if it's n minus 1 even, then there are more than one answer to the homogeneous. Okay, so we've now proven that unique solutions happen for the homogeneous system precisely when the rank is full. And equipped with that, we can now prove something really nice. We can prove the following. Let's say we have a matrix where the number of rows is less than the number of columns. Then the homogeneous system has non-trivial solutions. So remember, the rank does not exceed the minimum of the rows and the columns. So if the rows are less than the columns, that means the rank is less than n, so the rank cannot be full, which means that the homogeneous system has non-trivial solutions. And as an example of this, here you go. Here is a system with 2 rows but 3 columns. So by this proposition, we now know that this has a non-trivial solution, right? The number of rows is insufficient, right? And that makes complete and utter sense because 3 variables, 2 equations. I can't solve for those 3, right? I don't have enough equations to help me solve. So if you don't have enough equations, you cannot solve. So again, this proves intuition, which is really nice, right? Intuitively, before we even got into this class, if I gave you this and said, okay, can you solve this? Your answer should have been, well, yeah, but I'm going to get you more than one answer. Are you okay with that? And the answer now is, I have to be okay with that because that is always the case. So that's really nice. This is really good, what we've just proven here. This is a good spot to take a beat and really appreciate what we've proven. Because what we've proven is that our mathematical intuition doesn't lie to us sometimes. Right? Our intuition on this is, okay, I have too many unknowns and not enough equations, so I couldn't fully solve this. The best I can give you is like, well, all the answers look like this. Pick your favorite one. And this tells us now, in no uncertain terms, that that is what will always happen. So that is really, really nice. So it's always good when the intuition we have, when our daily experience of mathematics actually is what the theory says. So in theory, right, the theoretical says that there is a non-trivial solution, and in the mathematical practice, right, that's what we experience. So it's really nice that our practice lines up with what the theory says. So unfortunately, it doesn't happen in math. Sometimes you get theoretical results that are non-intuitive or seem to go against practical experience with mathematics. And then, right, so you get some nice cognitive dissonance, and you got to figure out what the hell's going on there. Because again, the theory, right, this is taking place in math heaven, where everything's nice and perfect. This right here, though, is math reality, where you actually have some damn numbers you need to work with. But it's not too bad. Okay, so yeah, it's really worth appreciating this. That when mathematical practice lines up with mathematical theory, that is always a good thing. So that's good news. So this is a good, even though, right, the proof is like literally a sentence, it's a very powerful sentence, which does happen a lot in math. Oh, side note, fun little bit of math lore. What the hell's the name of that theorem? It's like Fermat's theorem on 2 primes or something like that. Anyway, there's a very famous one-sentence math proof. I think if you just Google one-sentence proof, you'll find it. That's a neat little bit of math lore. So check that out. Okay. Anyway. I don't want to try to, since I'm pre-recording this, if I try to like open up another program while I'm recording this, I'm sure it's going to crash, so let's not do that. But you should do that. Okay, cool. So that's really nice that we've got this. And so let us now continue and finally prove something. So we now prove that so as we've seen, if your rank is full, that means Ax equals B has a unique solution. Let us now prove the reverse of that, which is, let's say your rank is not full, then there are distinct solutions. And as we've already proven, if you have 2 solutions, you must have infinitely many. Okay. All right, so let's actually prove that now. So then we will have full out that the only way Ax equals B ever has a unique solution is if, first of all, of course, B lives in the column space, which again we are just outright assuming from this point forward for these slides. But the uniqueness then can only happen if the rank is full. So if the rank is deficient, so if the rank is less than n, what's going to happen? All right, so let's prove that there has to be 2 answers flying around here. So first of all, we know we have at least one answer because B is in the column space. Now, what do we know? Since the rank is deficient, the rank is not full, that means we have a non-trivial solution to the homogeneous system. So I have a non-zero vector so that A times U is equal to 0. Okay, I want to create 2 solutions and need them to be different, so I will let x2 equal x1 plus u. Now, u is not equal to 0, so x2 and x1 cannot be the same. So I have 2 distinct entities here, so that takes care of that part. The only thing I need to verify now is that there's solutions. Who's busting in here? Charlie. Hey, what's up?
Hi.
Hey, I'm recording right now. Can you let me finish this and I'll play with you?
I want to play. I just want to go outside.
Okay, we can go outside after I'm done, okay? Okay.
That's not okay.
That's not okay. Oh, no. Okay, I just gotta finish recording this, then we'll go outside and play, okay? So give me, like, 15 minutes?
No, not 15 minutes.
Okay, how about 20?
No,
Charlie.
I just like 7 minutes.
Oh, okay. Alright. Sounds good. Alright, can you go back downstairs then?
Yeah.
Okay. Alright, bye. Close the door. Yeah, everybody is sick in my house. Except for our daughter, which is great. It was a good time. Alright. Alright, and there's like the smallest layer of snow outside, so she wants to go play in that. That's gonna be gross. So, anyway. Okay, so we're trying to prove that if the rank is not full, then there are distinct solutions, and thus there must be infinitely many. Okay. Being in the column space means that we have a solution. And now if the rank's not full, we know that there is a non-trivial solution to the homogeneous. So we do homogeneous plus the solution I've already found. Where have we seen this before? Note that this is non-zero, so x2 and x1 cannot be equal. And if I look at a times x2, matrix multiplication is linear, so it distributes the way you want. This is equal to b, because b is in the column space, and that's where this x1 came from. And hey, this is a solution to the homogeneous, so that's equal to 0. And there we go, we have two distinct solutions to ax equals b. So note the little trick, adding a solution to the homogeneous to a solution we already knew. We've seen this before. Cool. Alright, so with that, we now find that having a deficient rank guarantees more than one answer, and as we know, that means there's infinitely many. So we can now outright say the following. A matrix is of full rank precisely when the matrix equation actually has a unique solution for all elements of the column space. So there we go. Trying to actually solve ax equals b. Our goal, our hope, is that ax equals b happens precisely when you have a unique solution. Okay. And now we see that the only way that could have ever happened is if the matrix was in fact of full rank. Right. So unique solutions to ax equals b can only happen if the rank of our matrix is full. So the rank is equal to the number of columns. Beautiful. There we go. So that gives us a nice full-out answer on when can ax equals b be solved uniquely. Alright, well again, it can only be solved if b is in the column space, and now the uniqueness can only happen if the rank is full. So we're very happy about this. So there we go. Trying to solve matrix equations, systems of linear equations, we now know that if you're going into that, the optimal situation would be the matrix has full rank. Alright, so that is the optimal case, the optimal situation. If our matrix is full rank, then we clap, we stand up, we salute the flag, we're very happy. Okay. Now, the story's not over, because there's still a lot more ins, outs, and what have you. So, note that we're asking matrix full rank for a solution in the column space. So it would be useful to know when the column space actually can be replaced with Rm. Right, because again, when you set up ax equals b, A is an m by n matrix, x lives in Rn, and b lives in Rm. So as we've already noted, solutions only happen if you live in the column space. So it would be nice if we had some sort of similar result here, but we replace the column space with Rm. And it turns out that you can replace the column space with Rm when the rank is the number of rows. So, in other words, if the rank of A is equal to its number of rows, then the matrix equation has a solution. Note, I didn't say anything about uniqueness here. Has a solution for all possible right-hand sides, so for all things that are elements of Rm. Okay. So note the difference. Here we're talking full rank guarantees unique solution for everything in the column space. And full rank, remember, happens when the rank is the number of rows. Here we see if the rank is the number of columns. If the rank is equal to the number of rows, then the matrix equation can always be solved. Not uniquely, but can always be solved. So it is possible that your rank is M, but it's not full rank. So you can always solve it, but you can't do it uniquely. So that's a good situation to be in. All right, and now how do we prove this? Well, this is an excellent time to remind ourselves that A times X is really the output of a linear mapping. So note, the range of the linear mapping, which is the column space, is all of Rm precisely when the rank is M, right? We prove that. This linear mapping is onto precisely when the rank is M. So Ax equals B is a solution precisely if you're in the column space. That means that the matrix equation can be solved precisely when the column space is all of Rm, or in other words, when the column space, when the range of our linear mapping is all of Rm, which can only happen when the rank is equal to M. Right, so this is basically just a rewriting of an if and only if we already established, which is the range of this linear mapping is all of Rm, precisely when the rank is M. The range being all of Rm means the column space is all of Rm. Now, if the column space is all of Rm, then Ax equals B can always be solved. Okay, beautiful. So, these two results now are basically two results telling us an if and only if about solutions of matrix equations in terms of the rank of the matrix. If the rank of the matrix is equal to the number of columns, which we call full rank, then Ax equals B has a unique solution for all of them with column space. If the rank is equal to the number of rows, then the matrix equation can always be solved, regardless of what the right-hand side is. So, the absolute perfect Duke of New York #1 situation would be if the rank was not only equal to the number of columns, but was also equal to the number of rows. Because if it's equal to the number of columns, Ax equals B has a unique solution for anything in the column space. And if it's equal to the number of rows, that means Ax equals B can be solved for anything. So the column space can just be replaced with Rm. Note, in order for that to happen, we would need that the number of columns and the number of rows were equal to each other. So now, hopefully, other than the fact that they're nice, now we see why square matrices play a humongous role in studying linear equations, and why you pretty much always want your matrix to be square. Because now, if you have a square matrix with full rank, then you can guarantee Ax equals B can be solved uniquely for all B. Isn't that just peachy? Indeed. So, the prevalence, the reasoning why square matrices play such a huge role in studying systems of linear equations, they are precisely the situation you want to be in. You want your rank to equal the number of rows, and you want it to equal your number of columns, because then Ax equals B can be solved uniquely for all B. So, you got to be a square matrix in order for that to ever happen, so there you go. So if you have full rank, then Ax equals B has a unique solution. And furthermore, because you are in the square situation, we get away with a couple of other nice results. If you know Ax equals B has a unique solution for all elements of the column space, then you can guarantee full rank. So note, the rectangular, right, so note that is for free, we already know that. But the next one is the more powerful one. If you know that Ax equals B actually even just has a solution, then you can guarantee full rank. Note, in a rectangular matrix, we cannot get this. So, point 2 is just for free, right? If you know you have a unique solution, that means your rank is full. So that's just rewriting something we already know. 3 is the more surprising fact, because again, this is something that does not work for rectangular matrices. Right. So let's see this. So by hypothesis, the rank is equal to n, right? Because this means a full rank, number of columns. But the rank is not only equal to the number of columns, it's also equal to the number of rows. So the column space has dimension n, and since the column space is a subset of Rn, that means the column space is Rn. And since we are full rank, that means we know Ax equals b has a unique solution for all elements of the column space. The column space is Rn, so we're happy. Okay. Alright, so then as I noted in point 2, the hypothesis that Ax equals b is a unique solution, that just means you have full rank, right? We've already proven that this is equivalent to being full rank, so it's just worth reiterating it. We did change the sizing here from rectangular to square, so just worth reaffirming that. Okay. Now, the next one is a more interesting one, because again, this is what's not true for rectangular. If you know that you can always solve this, that does not mean your rank is full, it just means your rank is the number of rows. Possible your number of rows is less than your number of columns if you're rectangular. However, if you're square, they are equal, so we must be full rank. And there we go. So here we see square matrices is the place to be. Because full rank is really nice. It guarantees unique solutions for Ax equals b for all possible right-hand sides. So there's no having to restrict our attention to the column space. That's really nice. And also that's not too shocking because as we've already proven, an n by n matrix is a linear mapping from Rn to itself. A linear mapping from between two vector spaces of the same dimension is one-to-one if and only if it's onto. So, there we go. All right. And the real power here is really this last one. This last one's a really nice result because, again, this is something that's not true for rectangular and is only true for square. If Ax equals b can be solved for any b, then the rank must be full, which then we know that solutions we found had to actually be unique. That's really nice. So for square matrices, you actually don't need to worry about uniqueness, you just need to know that you can solve. The uniqueness then comes for free. That's really nice. All right, so again, another point in the favor of square matrices and why they play a very significant role and why we want to always be in the square case. Yeah, cool. All right, so to wrap things up for today, as we saw 12 minutes ago, I just promised my daughter I'd play with her in 7 minutes, and so I'm already lying. That's great. And she doesn't understand time. It's fine. I like that she went with 7 minutes. That's a weird choice. I was trying to go above. She said 15. I said 20, and I wanted to see if she realized that was more, and she did. Great. But she had 15. Whether or not she knows it, she was like, all right, let's go 7. That's halfway in between. She art of the deal right there. That was, there you go. All right. So anyway, all right. So we've now seen that full rank is what we want. All right, if you're full rank, we're very happy. Because then Ax equals b can be solved as best as it possibly can be. All right, but, right, that means you need your rank to equal a very specific number, and if I were to just give you a matrix, right, so if you were to do some data collection, you would just get some random matrix. The odds that its rank actually is full, they're small, depending on how many columns you have. If you have thousands of columns, you need your rank to equal the number of columns. Well, there are 1,001 possibilities, so more than likely, the matrix you have does not have full rank. So what happens in that scenario? Because unfortunately, as I learned in 2014, when the Rangers did not win the Stanley Cup, sometimes you don't get what you want. At least I got to see him get to the Stanley Cup again. After, yeah, so... That was it. That was it for Lundqvist. That was the only time he was going to get it to win the cup. Oops. And now, yeah. So we'll see. That series too against the Kings, right? Right. The Rangers lost that series 4-1. If that sounds like they got their asses handed to them, they really didn't. It's like almost all those games went to overtime, so it was like we could have won maybe. I knew we weren't going to win going into that. I'm like, yeah, I know we're going to lose, but oh well. Anyway, so right. As like in most things in life, you don't get what you want. But the good news is, in systems of equations, Ax equals b, it's all right if the rank isn't full, because we can still actually tell you something. Given a matrix, let's say your rank is strictly less than n. Okay, well that means your null space is non-trivial, right? Because again, full rank means the null space is trivial. So that means you can find a basis for it. It has some number of elements in it. Note the number of elements it has is what exactly? So remember, rank plus this number of elements is equal to n. So h is n minus the rank. And anyway, so yeah, you can find a basis for the null space that has stuff in it. Take any element out of the column space, so the things that you can actually solve Ax equals b for, and let's say that you've got a particular solution. Then every solution of the matrix equation is of the form, hey, that plus that. So solution to the homogeneous plus a particular solution. So we've already seen and discussed this, but here it is now written in full out gory detail. So before, when we talked about that, where you get your solution to the homogeneous and you add it to your particular, that gives you all possible solutions, we hand waved that big time and basically went, okay, well, sure, that's true, but is there any control over any of those things? Right? Is there any control over the number of things in the homogeneous? There is, and in fact, the number of things that show up is dependent on the rank of your matrix. So there we go. Beautiful. So here we go, a full-out description now. The homogeneous solution plus the particular gives you the general, and there we go. And here is a full description of how it goes down. Okay, so let's prove this. Let's say you actually have a solution to the matrix equation. I want to show that it equals something like this. Okay. All right, well, that means Ax is equal to b, which is equal to a times p by hypothesis. So a times x minus p is equal to 0. So x minus p must live in the null space, so it's got to be some linear combination of these basis elements. And so add the p over, and there you go. X is equal to some linear combination of the basis elements in the null space, so some solution to the homogeneous. I don't know what, but I know that it's some solution, plus a particular. And there we go. So, hooray, that thing we saw and talked about, solving the Ax equals b, means getting the homogeneous solution and adding a particular solution to it. We now have a much more precise explanation of what the homogeneous thing looks like. In particular, it's some linear combo of a basis for the null space, and the number of elements is controlled by the rank. Nice. Beautiful. So there we go. We're pretty happy with that. And now, equipped with this, let's wrap things up now. We basically have a full-out game plan of how to actually solve any consistent system of linear equations. So, obviously, you rewrite the system of equations as Ax equals b. Then, you find a basis for the null space in your matrix. Then, you find a particular solution. And then you're in two situations. If the null space was trivial, then the p you get is a unique solution, right? We've proven that null space is trivial, means rank is full, so if you have a solution, it's got to be unique. So, hooray. Now, if you actually got a basis for your null space that had stuff in it, then the general solution is any linear combo of basis elements plus the particular solution you found. And there we go. So, the story of solving systems of linear equations is slowly coming to an end. For any consistent system, we now have the following. You need to do two things. Find a basis for the null space, and find a particular solution. Once you have those two, you either know that there is a unique solution, and it's whatever the p is you found, or there is an infinite number of solutions, and they're all of this form. Okay. So, that gives you the blueprint of how to solve it. Which, by the way, if you don't know, How to Solve It is a very famous math textbook by a mathematician named George Polya. So check that out if you haven't ever heard of that. It's a fun book. All right. But where are we headed next? So we got some slides. Well, we still have to do two things. You have to figure out how do you get a basis for the null space, and you also have to talk about, well, how do you find particular solutions? Now, we could just say row operations and do that, but that isn't the full story. There's a lot more going on there. So our next couple of goals here is to talk about, all right, when you're trying to find a basis for the null space, what's really going down there? So we'll get into that, and that's the remainder of these slides. And then we'll talk about finding a particular solution. So note, you want to solve for x, and there's a part of your brain that's itching to do something. You're itching to take this and move it over to the other side, right? You want to divide that, right? Our basic mathematical practice is itching at us to go like, oh, just divide it over. Well, what does that really mean? We can't just divide what's 1 over a matrix. All right, cool. So that's setting up the stage for the next couple of things we're going to go after. So we're going to go down this rabbit hole and see where that takes us, and then we're going to shift focus on actually trying to solve for particular solutions using a very specific method. All right, cool. So with that, that is the story for today. So we'll pick this up tomorrow with slide 15. 15 minutes, exactly as promised. All right, see you next time.